Yeah. So what I've done today here on the blackboard is I summarized the main issues I wanted you to know about the subtleties of stochastic calculus. The proofs of all these results are not very difficult. They're usually just Taylor expansions. But they're not very well described in the literature. So at least I wanted you to have a list of points which I think are very important to know. And then if you want to use or study more in detail all these calculations, you can go to my notes, or you can go to one book, which I think, no, not now. Okay, which I think it's the best one for these topics, which is called, which is written by somebody called Oxendal. So let me write it here. Who's a mathematician, but the notation and the text is quite easy to follow. So the idea was to discuss with you, the problems that arise when you have an equation that doesn't have a second time derivative, only first time derivative here, noise, which is white, delta correlated, and I write it in this way, which is the mathematical way of writing these equations. And as I explained to you last week, this equation can be derived from studying a system coupled to an ensemble of oscillators, integrating away the oscillators, and then arguing that the timescale for the bath is the fastest one, so making the bath be white, and dropping inertia, because you are interested in long time regimes where the inertia timescale has been passed. Well, it's behind you. So time has to be discretized. This is my time axis, and I'm using tk as the integer index k times dt, the differential of time, so the length of these intervals over here. Now, this stochastic differential equation does not make sense, it's not defined, unless you say where you're going to evaluate this x here and this x here. So this is typically done by choosing an average between the value of x at the pre-point of the interval in question and the post-point of the interval in question. So say that k is here. This is k plus 1. So you're weighting with these factors alpha on 1 minus alpha, the value of x on these two extremes of the little interval you're looking at. So if alpha is equal to a half, this is a choice you make at the beginning of your calculation when you define the equation. Then you're working with what is called Stratonovich calculus. If alpha is equal to 0, then you're working with what is called Ito calculus, and you can choose any other value of alpha is good enough. Now, once you have chosen the alpha, the rules of calculus, for example, the chain rule for differentiation of a function of the stochastic variable x, are fixed, and are fixed to be of a peculiar kind. They are not the usual rules of calculus. Look, if this term were not there, then you have derivative of y with respect to x, derivative of x with respect to t, and this is the usual chain rule that you use. But if you have this stochastic equation, and you have an alpha which is not equal to a half, you have then an extra term that is proportional to this g factor, which is the one that multiplies the noise, and that is non-trivial. Notice that this term is present even when the noise is additive. If g is equal to a constant, and alpha is different from a half, this term is there. So you have to be careful when you do manipulations of functions of stochastic variables, even in the additive noise case. So this is something that is usually overlooked in the literature and in calculations. So the usual rule of calculus you only have if alpha is equal to a half for any g. Otherwise, you have to keep this extra term.
How do you define d in terms of the
Oh yeah, d is like a diffusion constant. So d is like temperature. It's proportional to temperature. Is the I changed my notation with respect to sorry, I'll call it dt. So remember that when I told you about the delta correlations, I mentioned that there was a 1 over dt here coming from the delta that is now transformed into a Kronecker delta, and V is playing the role of temperature. I'm just calling it D because it's the notation that is used in the, again, the mathematical literature in general. Thank you for asking, Lenka. OK. Now, something else I also said last week is that the stochastic processes that you get for different alphas are different. So if you integrate numerically this stochastic equation and you draw the trajectories for the x of t that you will get using alpha and alpha bar, you will get different ensembles. The distribution of the two will be different. And the way to prove this is very easy. It's just, again, Taylor expansion of what's the last term in the equation for an alpha minus the last term in the equation for another alpha. You will find that this is proportional to g prime. G prime in my notation is the derivative of g with respect to the argument, times alpha minus alpha bar, times dx, the differential of x over the dt, over, I mean, during the time interval dt, times psi. And this factor here is order 1, because this one is order dt minus a half, while this one, sorry, plus a half, and this one is dt minus a half. And they cancel, and it's order 1. Notice that this is true only if g is non-trivial, non-constant, what I'm saying. So this is true for multiplicative noises only. If g is a constant, then this difference is cancelled because of the presence of this factor g prime. OK, this you can prove. I mean, it's just very easy. Now, another important fact is that from the Langevin equation, you can derive a Fokker-Planck equation. If you want to go through the details, I can give you the notes, or we can do them together later in the afternoon if you wish. So anyway, the Fokker-Planck equation looks like the expression I gave you up there. So it depends on alpha, and it depends on g. You see the alpha over there and the g appearing in the two terms, actually. So this is another way of seeing that the processes are going to be different for different alphas, because there is an explicit dependence on alpha in this equation. Now you can ask, is there a way to choose the force such that for a different alpha, I get the same Fokker-Planck equation, hence the same statistical properties of my process? And this is very simple. I mean, you have to ask that that term over there, the one between parentheses in the first line, be equal to the drifted force plus the second term evaluated at alpha bar. And from here, you find which is the drifted force that you have to use for this equation to get the same Fokker-Planck equation, and hence the same time evolution for the two processes. Sorry, where? Alpha is here. Times alpha, yes. So there is always a way for this equation, and for other equations I will give you the recipe later, to find a way to make the two processes be the same, but at the price of changing the force. Now, you can ask another question. You can ask the question, which is the steady state towards which this Fokker-Planck equation evolves? So you go and look at the solution such that this term is 0 on the left-hand side, and then you solve for the right-hand side being to 0, integrating over x, as you usually do for usual Fokker-Planck equations. And you find that the steady state has the Boltzmann-like form. It's an exponential of minus 1 over d, and then you see that d plays the role of beta here. 1 over d is like beta. An effective potential. But then when you look at the form of the effective potential, you notice that it has this complicated form, let's say. where you have an integral over x prime. I'm not writing the differential, but there's an indefinite integral over x prime here, evaluated at x, where f appears, g squared appears, and then there is an extra term that looks like that. Notice that this one is present even for alpha equals a half. So one has to be careful with these issues at different steps. It's, you never really you're never really free of subtleties in these calculations. Now, if you want the effective potential appearing in the steady state to take the form of a potential that is independent of g, because here it depends on g, it depends on the function that multiplies the noise, right? And you would like to have a potential here appearing in the asymptotic weight to be independent of this g. So then you can look and see how do you have to choose the f such that you cancel the g here and you also cancel the g appearing over there. And then, OK, you find that this is the way to choose the force f to ensure that this uf becomes u. And here u is this prime means derivative of u with respect to x, like recovering a normal force here. So you see clearly how it works. This one cancels that one. This u prime appears here, but since it's integrated, it becomes u. And this other term cancels that one after integration. Yes?
Are both terms integrated?
No, the last one is not.
Okay.
So yeah, so let's write it like this. Yeah. Thank you. OK, so this is a way to find, yes? No. U is something external. I mean, it's the external potential under which you want to put your particle, let's say, in contact. So this U is here. So you see that the relation between U and little f is complicated. It involves G and it involves f, right? Yeah.
So g of x is a scalar function?
Yeah. I'm writing here for scalars. Because it's simpler. Of course, you can generalize this to vectors. That's the example over there, one example over there. But can be generalized to vectors, and then you will have indices and nabla operators, and it will look horrible. But, well, not horrible, but it will look more complex. Yes. So I'm doing just example of a particle on a 1D space to make it easy. So I mentioned this example last week, a concrete physical problem where multiplicative noise appears. And this is a problem of a magnet. So it's just a three-dimensional vector. And this three-dimensional vector follows this equation, which is due to many people, Gilbert, Brown, Landau. So it's the standard equation to mimic the evolution of a magnet under a field, external field. I call it deterministic here, just to say it's external field. Then there is a noise, and there is dissipation given by this term over here. So I told you last week that this equation conserves the modulus of the magnetization until here, the white part of the equation, only if alpha is a half. Only if you define what's on the right-hand side as evaluated with the Stratonovich midpoint prescription. If you wanted to conserve the modulus for any alpha, you have to add another term to the equation. So this is the equivalent of the drift in the equation for the scalar problem that I was discussing over there. You have to add this other term. It happens to be a constant for this problem, but it's not necessarily a constant, as you see in this other example over there. And once you add this term to the equation, not only you conserve the modulus of m as you want, but you also can show that the Fokker-Planck equation associated to this Langevin equation converges to equilibrium of the Boltzmann type with a potential which is what you expect, which is proportional. There are some constants. The mu appears, but I don't want to write it. So it's proportional to the scalar product between the magnet and the external field. So this is the magnetic energy that you want to have. So everything is consistent in this way. So I told you last week that in many numerical papers integrating this equation, people use Ito discretization. Why? Because in that way, the right-hand side is always evaluated at the pre-point, and then you can just construct the solution step by step. But if they don't write this term as well, the modulus of their magnet is going to decrease. I mean, it's not conserved. So it changes in time, and actually the modulus is decreased, so the vector disappears. So to correct for that, they renormalize the vector, but then you don't know what you are really doing. You don't know whether the dynamics is converging to what it has to converge at long times. So this is like a little bit dirty as a trick. While if you add this term, which is non-zero for alpha equals 0, so it has to be added for Ito calculus, well, then you arrange things. Another example, which is perhaps more interesting for the glassy people here, where these issues have been discussed, is the problem of, for example, Brownian motion, but in a confined volume. So say that you have your Brownian particle that sometimes go close to the boundaries because it's a small system, so there are boundaries. And then there's no reason to suppose that the diffusive constant, or the friction, better said, that the Brownian particle will feel close to the walls will be the same as the one that it will feel at the boundaries. So to modelize this kind of problem, typically you have to take a friction coefficient that depends on position. And since the position is the stochastic variable in this problem, then this corresponds to multiplicative noise. And then you have to be careful about all these issues that I'm telling you about. Okay. So, because you see, the friction is within the noise correlation, where I wrote over there, up there, xi psi proportional to d. In d, there is a friction coefficient as well, that typically one sets to 1, but it's not 1, it's something. Exactly. So let me write it here. So the noise-noise correlation has a gamma naught here. And we usually don't write it because we assume that there is a reparametrization of time. We eat it up in a renaming of time that it's this gamma naught. But the gamma naught is there. So if it's position dependent, you cannot do this transformation. You have to keep the gamma naught. And the equation I wrote over there should be written gamma naught dxt equals to f plus g times psi. The gamma naught is here, it's also there in the correlations of the noise. So this is like if you, instead of talking about the noise, you talk about eta, you rename the noise, then the gamma naught will appear here, and it will appear here. And it will be the multiplicative noise.
I missed the comment about why gamma depends on R.
Because if you have, imagine that you have a Brownian particle in a small space, in a small volume, confined to some cavity, but it's pretty small. So then you have the walls, right? You have the container will play a role in the motion of the Brownian particle, because it will typically go close to the boundaries, your Brownian particle. So then a way to take this into account, say the potential acting, the potential acts on the fluid, and the fluid acts on the particle. So you need to take into account the R dependence of the gamma naught.
Once you define it, it's confined. Everything depends on.
Yeah, that's right. Yes.
Is there a physical interpretation of that drift term?
Of the drift term? This one here, you mean? I wouldn't give it a physical interpretation. I would just say that it's part of the mathematical definition of the I missed you. Where are you now? Yeah. It's part of the mathematical definition of the equation, to write a correct equation that describes your physical problem. And for the physical problem, the important fact, to my understanding, that you have to impose is that it should be able to reach thermal equilibrium. Then, of course, it may take very long for it to do it. There could be reasons, relaxation times that go beyond limits and so on, that don't allow it to reach to equilibrium. But the starting equation should be such that the system should be able to reach equilibrium. Otherwise, you are taking it out of equilibrium from its mere definition, and that's not nice. Yeah. So I think you have to put a little bit of physical intuition into the problem to write the initial equation and add this term. Okay, so I'm going to, if there are no more questions about this, my plan for today is to sketch very briefly, because unfortunately I don't have the time to do the derivations on the blackboard, functional formalism that allows us to go beyond the solution of simple problems like the P equals 2 spherical model or the ON model I showed you again last week. So it's a functional formalism, what I want to show you. For those of you who know, it's very similar to the Feynman path integral. Formalism, and it has a lot of advantages with respect to trying to solve the Langevin equations directly, which is typically impossible, which is that it's well suited to establish perturbative expansions. Time-dependent RG calculations, the ones that I told you that were good to study critical dynamics, like, for example, in the domain growth problem. Self-consistent approximations as well. These will be the ones that will allow us to derive equations for P larger than 2 spin models. The ones which are interesting for glasses. And also exploit dynamical symmetries that allow us to derive exact results, some exact results, for systems in and out of equilibrium. And for these are fluctuation dissipation theorems and what in the literature are called fluctuation theorems, which are or have been very popular. I will not discuss them very much in detail today, but I just want to tell you that from this formalism, functional formalism, is very easy to derive these results without a lot of effort. But one has to be careful again about all these issues, about discretizations, alpha prescriptions, and so on and so forth, to do the proofs correctly. Now, what I would like to do is to switch on the it's there. So the only thing we have to do is the screen. And maybe the lights, I don't know how. Okay, thank you. So, okay, I said already I'm not going to go into the details of the derivations of these functional integrals, but if you want to go and look at a paper where we do it with a lot of care and we also summarize other approaches, you can go and look at this paper over here that I wrote recently with Vivien Lecomte. where special care of discretization effects were taken. So the key words here are Onsager-Machluk formalism, or Martin-Sigia-Rose, Jans and the Dominicis formalism, which are, as I said, very similar to Feynman path integrals. So what's the idea? The idea is that if you have a stochastic processes, you will have sorry. Right. So you will have random trajectories generated by this stochastic process. So imagine that you start from some initial condition, say x0, and well, you draw one trajectory. You start again. You draw another trajectory. You start again. You draw another trajectory, and so on and so forth. So at each time, t, you will have a distribution of possible x values that the trajectories will realize at this time t. This, of course, depends on the noise, and it depends on the initial condition, and it depends on the equation that you use to generate these trajectories. The initial condition itself, it can be distributed with some distribution function. So I'm going to call it pi of x0, the distribution of initial conditions. And given an initial condition, I can go and evolve my problem. And what can be done with this formalism is to write a probability distribution of trajectories. So with these curly brackets here, I'm representing the ensemble of x1, x2, x3, xn, let's say, where x1 is equal to x of t1, and so on and so forth. It's just a notation to make it short. So what I'm writing here on the left is the probability distribution of these trajectories giving alpha. For each discretization, I will get a different probability distribution, actually. Now, how do I do to evaluate this probability distribution? Here, for convenience, for what I'm going to tell you later on, the initial time, I called it minus tau, because for the issues of the symmetries that I mentioned, it's more convenient to work with a symmetric time interval. But this doesn't change anything, of course. So minus 2 in this notation is the initial time. And in the notation, say that I evolve until plus 2, which is the final time. But this doesn't, well, it's just an issue of notation at this step, at this stage. Now, the important part is what is here. So here, I impose with a delta function that the values of the x's that I have at the different times, so k is the index of time, like in my sketch over there on the blackboard, up blackboard on the left, so that the values of the x's that I evaluate on the left are solutions of the Langevin equation. So here, this means that this is a solution of the Langevin equation, and I want to see, how many times with the deltas I get these x's on the left that correspond to solutions to the Langevin equation. And this I have to average over the noise. So these angular brackets here are averages over the noise to get the distribution. So, okay, this is just the formal definition, if you wish, or just natural evaluation of this probability that I want to obtain. Now, what is the solution to the Langevin equation? I can write the Langevin equation in this form. So I discretize it, and I look at x at time step k. It will depend on x on the previous time step, on the noise at the previous time step, and on alpha. But this equation can be implicit, you see, because if I'm using alpha discretization, a generic one, the post-time step appears also in the right of the equation, in the right-hand side of the equation. You see what I mean? Everybody sees what I mean? OK. So this equation can be implicit, so it can be difficult, maybe impossible, to write explicitly what is xk as a function of xk minus 1 and the noise at the previous step. But it doesn't really matter for this construction. Now, the integral can be computed if you, again, implicitly write, or this one you can do it explicitly, if you rewrite the equation by taking psi of k minus 1 as a function of the other three things. So very in a sloppy way, what I'm doing is I'm writing this equation like this. Of course, taking care of where I'm evaluating this one, that one, and this one over here. But this I can do. So in this way, I write psi of k minus 1 as a function of x of k minus 1 and x of k. Now, if I want to rewrite the delta function that here acts on x as a function, as a delta function that I interpret as acting on psi minus something, so the equation written in this way, psi minus L, I need to include a Jacobian of the transformation in the delta function, right? It's the just generalization of this trivial relation between functions, normal functions, only that here I have to think that I'm working with a vector, because the psi, the x's, and the xi's evaluated at the different time steps, I can think of as being vectors. So it's just the generalization of this Jacobian here, of the change of variables within the delta function generalized to vectors, that gives me a Jacobian, which is the determinant of a matrix. Now, computing this Jacobian is easy for additive noise. It's not so easy for multiplicative noise. What we do in this paper with Vivian is to, well, present a way of calculating this determinant for multiplicative noise and discussing how it compares to other ways that people have also presented in the literature before, and well, discussing relations and so on. I don't want to go into the details of that. It can be computed, even for multiplicative white noise. It can be computed in detail. So once you do that, you rewrite the distribution function with this j appearing there, the delta now separating the noise as a term, the right-hand side of the equation, and the initial distribution. And now the integral over the noise can be performed, because you see there is a delta here, and the weight that gives you the distribution of the noise is a Gaussian factor with the correct normalization, but it's Gaussian noise, because this is what I'm taking for the noise. So this integral that corresponds to this average over the noise can be performed. You go ahead, you do the calculation, and what you get is a form of this kind, where I'm writing an action, and I'm introducing an auxiliary variable, which I'm calling, again, it's a vector. I'm calling it I. I is the I of the complex numbers, and x hat. So I have another vector here. This one has disappeared because I've integrated over it. And I exchange it for this auxiliary variable x hat that is just used to rewrite the delta as an exponential. The only thing I'm doing is the delta that was here I'm using it as an exponential, using well, the extension of the relation which is over there. And whatever remains, everything that remains after integrating over the noise, exponentiality in the delta, and putting the Jacobian also in the exponential, is an action that looks like this. So it has the contribution of the initial conditions that I just wrote as exponential of log of pi, because it's handy to have it in the exponential. An integral over this auxiliary variable that multiplies all this up to here, a term which is proportional to the auxiliary variable squared times gt if I have multiplicative noise, and this comes from the Jacobian. Yes?
Why do we need to write the delta function this way?
And you don't need to write it this way, but it's convenient to have the form of the action written with this auxiliary variable, because in this way you can identify very easily what is the response function. This auxiliary variable allows you, and this, okay, it's 2 lines to prove. If you want, I can show you the proof later, but it's very easy to prove that the linear response function is just equal to this quantity here. So sometimes this auxiliary variable is called the response field. This is what makes the difference between the Onsager-Makhlouf formalism that integrates or doesn't introduce the x-hat directly, and you directly have the distribution without this integration over there. You see, you can perform the integration because x-hat is also quadratic. So the dependence on x-hat, you can, eliminate it very easily by integrating over x-hat. But it's more convenient to keep it because, like this, you have an access to the linear response function in your problem in a very easy way. And this is the key point of the Janssen development in the 70s that realized this. Yes.
This is what you get just by doing like Hubbard-Stratonovich.
Yes, exactly. You can think about it as Hubbard-Stratonovich transformation. Yes. Just, oh, okay. Yeah, yeah. G inverse where, sorry? Oh, here. Oh, yes, probably. Yes, yes, yes. Yeah. Thank you. Here? I don't think so, but the G inverse after calculation, which is, a lot of steps, but after calculation, the G inverse will come here. The G inverse, yes. The Jacobian gives you just this.
So the equation here is the EQ is now FT plus GT CT.
Say it again, sorry. The
What you call EQ
EQ
in the previous slide.
in the previous slide. Ah, equation. I called equation.
Yeah.
Okay.
That equation is the equation for the stationary state of the logic.
No. There is the equation. I use EQ for equation. So what I mean by EQ there is just this. Well, I can erase here. What I'm calling EQ there is just the equation written in the form like this, discretized. So the right-hand side, this is ek. Right? And then when I talk about L, is what I wrote over there. So L is just inverting. This is what I call L. Say it again. Sorry.
Roughly speaking, the Jacobian is just a product of G's over X's over.
Yes, exactly. Well, but no, you have a product here. So here, this is a big matrix, you see. Now, the matrix is very sparse, of course, because it's only coupling. This matrix over there only couples k minus 1, k, and 0. Do you see what I mean? Because of the Markovian character of the noise, on the right-hand side, everything is evaluated in k minus 1 or k. No, there's no information about the past.
There's also implicit differentiation of X's with respect to noise, right?
This is here. No, but this you can is. Yes. Yeah. X depends on the noise, but it's only explicit variations that you have to take. It's only the explicit variations that you have to take here. So it's only here that you have to variate with respect to psi.
But then how does psi at time t plus 1 depend on psi? You know, if it's a short-range correlated noise,
Yes.
then there's no correlation between.
Right. It will give you deltas that then will tell you something about where you have to evaluate the x's.
It's just a G. G is just a
Yeah. It will give you a g, but then you have to do this calculation. We can go through the details, but it's for the multiplicative case, it's particularly heavy.
Can you say that the Jacobian is simple for the additive noise? Is it just the constant?
No, it's just this. It's again, it's the f here, but since you don't have to worry about drifting the f, then just is the derivative of f, which is the second derivative of the potential. So for the additive noise case, I think I have it in the here. So this is the form for the additive noise. Let's just focus on the additive noise. So there are g's that disappear everywhere because g is a constant. The force is just the derivative of the potential. So there you have the Jacobian. This is the equation, the equation you started from. This is the L, what I called L. And this is the square of the hat, and this is the hat. But you see that there is still a dependence on alpha that accompanies the Jacobian. And many times in the literature, you don't see this one. Why? Because implicitly, it's thought that the process is evaluated in the Ito formalism, because then alpha is 0. But I told you there, maybe I erased it now, that the chain rule for the alpha equals 0 scheme is non-trivial. So if you want to do calculations with this action without this term, and you are in Ito, you have to be careful and you have to keep the non-trivial chain rule in your calculations. Otherwise, you make mistakes. Yes?
Just two common questions. So, have you ever written, if I integrate out over the response field,
Yes. You got the square root of this one.
there should be a t in front of, there should be a friction coefficient in front of dx dt, otherwise you won't get it.
Yes, but now I set it to 1 in this case, the friction coefficient. Sorry?
If you set it to 1, what is the just temperature?
Temperature. Yeah. Just temperature.
And the other question is, if you go back to the multiplicative case,
Yes.
I don't see why there's a g missing. Because quite explicitly, I mean, at the least, your Jacobian going from x's to x's has a g. You know, because x is multiplied by g.
Here, you mean?
Well, like if I look at the equation of motion,
OK, so let me check it. Perhaps I'm missing one, but yeah.
I mean, maybe I'm wrong, but I just see g xc as x.
OK, let me check this. Well, it will take me a moment to find it, but OK, I can check that afterwards.
Just, if I just look at that equation of motion,
Yeah, no, you're right. You're right, absolutely. So let me see. I have it here. X hat dt minus f.
probably missing.
I'm definitely missing a 1 over g here. No, you know what? Yeah, OK. Yeah, I jumped over a step. Sorry for that. So I copied, yeah, there is a 1 over g missing here, and I made a mistake by copying different expressions on the slides. So what I've done to write this term here, only that I forgot to do it over there, is to rename the auxiliary field. Sorry for that. Yes. Yeah, this is what I've done, but I did it in this, and I forgot to erase it over there, and I forgot to tell you. So yes, absolutely. Thank you for that. And this is a change of variables in the path integral, and this is the one that gives you the response. Otherwise, there could be a g as well. Thank you for that. Yes. OK, so OK, this is it. So once you have, so let me go to the additive noise case, which is not yet this one here. So once you have the action written in this way, you can compute averages, right? What you want to do is to compute observables as averages over the noise of functions of x and the auxiliary field. And this can be done in the usual way as a path integral. So you have to integrate over all the trajectories, all the realizations of these auxiliary fields, the weight, and the function that you want to average. In the weight, there is information about the initial condition. There is information about the alpha. And I included a lambda here that represents all the parameters that could be present in the potential. In the potential could depend on the, I don't know, if it's a harmonic potential, I could have that the potential is something like this, and the lambda is the spring constant in the potential. But there could be other parameters, so I just wrote them here in this way. Why do I do that? Because I can come here and tell you without proof, because I don't have time, that there are changes that you can perform in the variables x and variables x hat that allow you to prove exact results for the situation where your system is in equilibrium. So what does equilibrium mean here? It means getting the initial conditions from equilibrium, if you choose your initial conditions to be drawn from this distribution, and you use the force that corresponds to minus u prime of x in your equation, the same u here as here. You're setting your evolution in conditions such that the system can equilibrate, or starts from equilibrium and remains in equilibrium, better said. In that case, you can prove that this action is invariant under this transformation. I'm using under labels for the time dependencies, and alpha going to 1 minus alpha. So this is an invariance, like a generalization of time, time reversal, because I'm changing t into minus t. So you see here, this is like time reversal. But on top of doing this time reversal transformation of the physical variable, I have to do a transformation of the auxiliary variable that adds this extra term. Beta is inverse temperature, or 1 over d. But I also have to change alpha into 1 minus alpha. Otherwise, this Jacobian term that depends explicitly on alpha, this one here, will not work correctly under the transformation. Under this transformation, the action that I have here remains equal to the action that I have there. The integration measure as well, and the integration limits as well. So this is an invariance of this problem. And by exploiting this invariance, one can, for example, apply it to the observable x of t I x hat of t prime, and see what it applies if I apply it here. So I will get x of minus t I x hat of minus t plus beta dt of x of minus t. And if you look carefully at this expression, you will see that sorry, I forgot the primes here. You will see that you can rewrite it in this way if the correlation function that I'm writing here, this is the correlation function, I assume it can be rewritten from minus t prime to plus t prime. So under the time reversal of the correlation function, I rewrite it in this way. Otherwise, I keep the minuses everywhere. This is the fluctuation dissipation theorem of equilibrium, a relation that holds for any system. You see, the potential is not here. Any system in equilibrium should satisfy this relation between linear response and correlation functions. I can go beyond this and use this transformation in cases in which the symmetry is broken. So how can I break explicitly this symmetry? By using potentials that depend on a time-dependent parameter, for example. Or by using initial distributions that are not of the Boltzmann kind. For example, using initial distributions that are of the Boltzmann kind, but using potentials that depend on time-dependent parameters, one derives fluctuation theorems exploiting this transformation that is no longer a symmetry, but it generates terms because the action will not be invariant under this transformation any longer in this situation. But the extra terms are going to be the things that appear in these fluctuation theorems, okay? Which are exact results for out-of-equilibrium systems, explicitly out-of-equilibrium systems, because are taken away from equilibrium, for example, by these time-dependent forces or non-potential forces as well. So I don't have time to discuss this in a lot of detail, but I just wanted to mention it here. OK. So now half an hour to discuss the dynamics of the p-spin. Yes. Yes, please.
In order to have a reversal invariance, it is necessary that the initial distribution is equilibrium.
Absolutely. Because in this way, if you want, we can go through the calculation later. But the trick is that by translating this hat term here by something that is proportional to the derivative of x with respect to time, you build a total derivative here. You see, the dt that comes from here will combine with this one to build a total derivative. But you have to be very careful about the calculus that you're using, because if you're not using Stratonovich, if you're using alpha generalized scheme, then dt of x times dx of v is not the derivative of v with respect to time. There's another term. You take into account that other term, and that one will kill this one, will combine with this one. So everything works, but you have to be very, very careful about all this, using the good rules of calculus in the action as well. Other questions? OK, so how to derive, using this formalism, equations for the p larger than 2 model that we want to study. So let's be very sketchy about this as well. It's a choice. You can. I was using the plus sign. You see, I wrote plus or minus here because in your Fourier transform of the delta function, you have the liberty to choose plus or minus.
What I mean is, just as a definition for these equations, is it exponential?
I use it with plus. So I wrote it, I don't know where, somewhere. Over here, I wrote it with plus. POM is Onsager-Machtub. It's the name that is given to this formalism once you integrate away the x hats, or whether you don't introduce them from the start. So you can construct the distribution of the trajectories without need of introducing this auxiliary field, and this is what is called Onsager-Machtub formalism. The good thing about the x hat is that it allows you to go and look at the response functions as well, which is especially important when you have out of equilibrium situations. So again, the p-spin that I want to discuss. OK, let's go with this. This is the Hamiltonian we want to study for p larger than 2. So if p is larger than 2, there are at least 3 spins here. So this Hamiltonian is not quadratic. Hence, I cannot solve the Langevin equation associated to this problem directly. But what can be done is to write this formalism for this equation, for this Hamiltonian and for the Langevin equation corresponding to that, with additive noise, because there's no reason to work with multiplicative noise in this case. So you go and you write the Martin-Sijar-Rose action that will depend on S hats, and on S's, and on Z. Z being the Lagrange multiplier that enforces the spherical constraint. Recall that the S's are continuous variables, and the S hats as well. Now, what is the magic of these problems? When here you're summing over all groups of p-spins in the system. So when the problem is mean field, what we call mean field or fully connected, meaning that everybody interacts with everybody else. the magic is that one can introduce auxiliary matrices in time. In this problem, I will call them Q, A, B of T and T prime. These objects will be introduced via Hubbard-Stratonovich transformations or delta functions. There will be objects which are summed over all the spins, normalized by the number of spins, and they will take this form, where what I'm using as indices A and B are 1 or 2, and 1 will correspond to S, let's say, and 2 will correspond to S hat. So you see, I have 4 of these objects here with respect to these indices A and B. I can have S with S, I can have S with S hat, I can have S hat with S, or S hat with S hat. So, 4 matrices in AB space. Now, if I introduce these things in the functional integrals, I will be able to go ahead, integrate over the spins, because the spins will become now quadratic. Many steps will follow, and what will happen is that in the end, you will be able to write the action you will be able to rewrite that generating functional, if you wish, as an integral over the QABs of TT prime. So here, with this symbol, I mean that I'm taking into account the 4 possible values here and all the times. E to the minus n, an action, a new one, let's call it new, that depends on these QABs, T and T prime. But the good thing about this is that after all the steps that I'm jumping over and not explaining, there is an n here. And everything that is here is order 1 with respect to n. There is no more n. So what you can do is evaluate this integral by saddle point. You can go and see which are the values of the q's that minimize this action and hence give the most important contribution to this integral. And doing that, you obtain equations that will act on the q's. You can also prove in the same way that the q's are equal to their average values, the q saddle points, are equal to the average values of the q's. So the equations satisfied by the saddle points are the equations satisfied by the averages. But remember what were the definitions of these q's. The averages will be C of TT prime, R of TT prime, R of T prime T, and something that we call Q4 of TT prime, which is the average of the hat variables correlated between themselves. Now, this thing here can be shown to be 0 by causality. if I take my convention such that t is larger than t prime, this one is also 0 by causality, because the system cannot respond after a perturbation. No, sorry. The system cannot respond before the perturbation is applied. So here I'm applying a perturbation. Here I'm measuring with respect to the response. So this is 0 if the system has causal dynamics. So I'm left with only 2. Now, for these two, the equations look like Schwinger-Dyson equations, what people in field theory call Schwinger-Dyson equations. They have a relatively simple integral differential structure. I will write them in complete generality, and then I will make the p equals the p spin case explicit. So in complete generality, they look like, let's write it, no, let's write it this way. Well, I will have to check my sign, oh, let me check this one. I will check it in a second. Let me check the times. So this goes places D. This is another D, D bar, let's call it. T second. There it goes. Okay, so this is the structure of Schwinger-Dyson equations, what people call Schwinger-Dyson equations. Where I have to say what are these functions sigma, and d hat. So for the p-spin problem, sigma and the bar take this form. So they're basically powers of C, only that sigma is like a response function. This is what is called the self-energy. It's a response function in the sense that it's proportional to a response function and has the same causality properties as a response function. This is proportional to a theta function. This is also proportional to a theta function. And the bar is what is usually called the vertex. And I guess that perhaps there will be more details about why these things are called in this way. It doesn't matter so much. The thing is that with this couple of equations, plus an equation that has to be written for the Lagrange multiplier, that is the self-consistency spherical constraint imposed that yields that equation. I'm not writing it, but it's simple to write. It's an integral equation over Z.
Because C didn't depend on time.
It does. Z has to depend on time in the dynamical problem in the same way as when we discussed the ON problem and the p equals 2 problem. Z has to depend on time. Otherwise, you will get nonsense in the dynamical problem. So the difference is that the equation for Z doesn't have a time derivative. It's just an integral equation, but it depends on time. While these other equations here have this kind of inverse Green's function acting on the C and R, and these are time derivatives, and these are time derivatives. So all these problems of disordered systems with interactions and so on and so forth, in these mean field-like limits, can be set into equations of this kind. I didn't tell you much about the initial conditions. I didn't tell you much about the average over disorder. There are two important issues to take into account. The initial conditions will appear here. The equations I wrote in the left are the equations that correspond to random initial conditions. Let me write it here. These are the relevant initial conditions if you want to think about the problem of a quench from high temperatures to low temperatures and see how the system evolves after this quench. So then the information about the initial conditions is irrelevant because they are just random. They don't appear in the equations. But if you want to impose equilibrium initial conditions, for example, you can do it. But though that will yield extra terms in these equations that I'm not writing. Okay? But it can be done. Now, up to this step, the equations are very, very general. The sigma and the d can be anything, basically. Apart from the fact that you see from here that they look related, right? So they look related by this taken. If you take the derivative of this expression with respect to C, you get this prefactor here, and then you get the R over there. So they are related. They are not completely independent, these two objects. If the problem derives from a potential, like what we're doing there, if the forces, the deterministic forces, come from a potential, you will always have a relation such that sigma will be the variation of V with respect to the correlation times the response. And there will be this relation between the two. It's linked to the fact that forces derive from a potential. Okay. Good. Now, one has to solve these equations. So how can I put this up? How do I do it? Where is it? This one? No. Just do it for me, please. So now the question is how to solve these equations. So the first thing you can do is to put them in a computer, because you see that they are causal equations. Because I assume causality, one can construct the solution of these equations step by step in time. You start from 0, t equals 0, t prime equals 0, and you go ahead with your algorithm written with the correct discretization that you have chosen, and you can represent the solution in a sketch like this. This is the initial time, say 0, and the diagonal is equal times. I'm taking t larger than t prime, so I'm looking at this upper half plane only. Say that you choose the working temperature to be below the critical temperature for this problem. Which critical temperature? We will discuss it in a second. I will call it Td. Is the one that will play the role of Tg in the glass problem. Now, when I showed you results for the correlation functions in the coarsening problems, below the critical temperature, there were these curves that were looking like this. Right? This is the correlation, T minus T prime, and the curves corresponded to different T primes. So there was this separation of timescales between what the correlation does above QA and what the correlation does below QA. Here I have another quantity that I have to take care of, which is the response. This is a couple of two equations acting on two functions of 2 times, so it's kind of complicated. So what I can do is look at my numerical solution of the equations, those over there, and see how the integrated linear response, remember that I defined an integrated linear response as something that was the integral of the instantaneous linear response over a time interval going from T prime to T. So if I plot the chi here, I get something like this. So it also has a separation of timescales between, say, a chi A, where the behavior is stationary, and another regime where it's aging. And again, this is T prime 1, T prime 2, T prime 3, ordered in this way as here. So I have the same kind of separation of timescales between what happens for the correlation and the response. I have a non-trivial response in this second aging regime, contrary to what happened with the coarsening problems. And in this plot here, I can very roughly, so let's focus just on the upper plane, very roughly say that there is an opening regime where times are close and the dynamics is stationary, from another regime where times are far away and the dynamics is non-stationary. Okay, so this corresponds to this regime, one here and one there. Let's write it here. And this corresponds to this other regime here. I should have written the two below to make things clear. Now, I tell you that this is what happens if you go and solve numerically these two equations together. Now, can one find these results analytically as well? And the answer is yes. Using this information, what you can do is to write the equations in the different regimes. So basically what you have to do is to consider regime 1 and regime 2 separately. No, because I have derived these equations. This is something I didn't say, I should have said. These equations are valid in the limit n going to infinity, having already been taken. Because I have taken the saddle point in this limit, so n has gone to infinity. Times are always finite with respect to n. Sorry? No, this is starting from out of equilibrium. This is after a quench. Random initial conditions. So it corresponds to a quench from initial temperature infinite to working temperature T. Okay? So in the limit n going to infinity, there's lots of things going on in the relaxation of this problem at finite times with respect to n. Now, I lost my eraser. Yeah, here it is. Yes, please.
So all this is working this out for p equals to 2?
No, any p.
But then why isn't there, I would think you would have like a 2 to the p power.
Yes, here it is p. Here is p.
It's inside the subnet.
It's inside the self-energy and inside the vertex. So this is for any p. What is here is for any p. What is here is for p larger than 2. For p equals to 2, it would saturate this response.
Another question related to this. When you decouple the p-spin interaction after you have disorder, there's a q to the p terms, but
Yeah.
there's also, in principle, q to the smaller power than p.
No.
Way larger limit?
No. For the homogeneous p model, the one that has only this term in the action, there will be only powers of p powers. There will not be other powers. Then you can build models with different p's and get different powers. This is it. Exactly. It depends on which is the departing Hamiltonian that you have chosen. Now, I will not go into the details of how these equations are solved, but believe me, they can be solved. So what you have to do is to focus on regime 1 and write equations for C and R in regime 1. Focus on regime 2. Write equations for how the C and R's are coupled in regime 2. There will be couplings between the two, but since you see that the plateaus are sharp here, they're flat, you can decouple by making some approximations in the long time limits the two regimes. You can solve the equations in both regimes. So by doing that, you can obtain this behavior, that behavior, this behavior, that behavior. For the people interested in mode coupling theories, there are interesting exponents appearing here and appearing there. The way in which the correlation approaches this plateau and departs from that plateau make appear those exponents A and B of mode coupling theory that perhaps they will discuss. I don't have time to discuss. But it's just to tell you that this model, the P simple problem, has very simple exponents, but then you can, decorate a little bit the Hamiltonian and get all the richness of those exponents of mode coupling theory. What I want to say in the last 2 minutes or 5 minutes is how to interpret these dynamics. You've seen free energy landscapes. You've seen mostly potential energy landscapes, but I insist that you have to look at free energy landscapes. So you have free energy landscapes. Why this model has, in the infinite end limit, this non-stationary relaxation that goes on forever. This doesn't stop in the limit in which I have derived those equations. And the interpretation for that is that for this problem, you can derive, again analytically, the tap free energy landscape that Florent mentioned. So this is a free energy landscape that tells you how do the local magnetizations behave. So below, well, let's say, it depends on temperature. And basically, simplifying a little bit, what you have is that a very high temperature, this free energy landscape has only one minimum with all mi's equals to 0. When you start lowering temperature, there will be other minima, saddles, and structure that will appear. When you get very close to this TD, you have lots of these objects that appear. But more importantly, when you get close to TD and below TD, apart from this things that you have seen in pictures all over and all over again in this school and elsewhere perhaps, there is something that you haven't seen, which is a flat region. A flat region that we call threshold. And this is the attractor for the dynamics. The initial condition that is random, I said, started very high somewhere here in this picture. And it started relaxing because my system is coupled to a bath, so it relaxes. It could relax here, could relax there, here or elsewhere. It relaxes here. It's a fact. I'm not explaining why it does. I solve the equations, and I see that it does. How do I see that it does? Because there are many quantities that I can compute analytically from the dynamic solution that correspond to properties of this threshold. Say it again. For example, the value of this plateau here, this is a function of temperature, right? A function of temperature and P, the characteristics of the Hamiltonian. If I look at how this threshold is structured, if I look a little bit more in detail at this threshold, what I have to imagine, what I can also show, is that it's made, you can think of it as made of channels, but very flat. So imagine that you're on the mountains. You're on a plateau on the mountains, but it's a plateau made of channels. So there are some mountains that come above your plateau, but you can follow those channels. So the channels are flat. The bottom of the channels is almost flat. But then you have the direction in which you have the mountains, right? So this is the flat direction. I write it almost tilted because there is a little bit of a drift. And then there is this other direction where you have the mountains coming up around you. So the QEA is linked to the size of these channels, the transverse size of these channels. I can compute it here with a static calculation using TAP. I can compute it here with the dynamic calculation using all those equations. I get the same expression, which is different from the one that corresponds to these deep states, which are harmonic in all the directions. So this is one hint to the fact that you get to this threshold. There are other things that can be said. The fact that this dynamics doesn't stop. This dynamics in mean field limit, so in n going to infinity limit, it never stops. And it never stops because the extent occupied by this threshold is infinity in that limit. So I always have flat directions to follow and continue like diffusing along those flat directions, right? But it's a much more complex diffusion like the one of the ON model that I mentioned last week, where there was only one mode that was diffusing. The K equals 0 mode, I could identify that it was the diffusive one. Here I have to think in terms of phase space to start with. This is phase space, it's not real space. And it's extremely rich and can be studied in many, many details. Something else that I can say is that with these dynamics, adding extra terms that correspond to particular choices of the initial conditions, I can put the initial condition here, let's say. It's a different equation. It needs some extra terms. If I put the initial condition here, what I will see is that the correlation function between T and T prime does not go to 0. It goes to the Q of this state. Let's call it state. So these states are confining in the sense that the correlations approach a constant in the long T minus T prime limit and they don't decay from the constant. So there's no second relaxation. There's no aging. There's no second relaxation there. But to go there, I have to choose a special initial condition that knows about this state. Any typical initial condition from high temperature will come here. And it will not get there in finite times that are the ones for which these equations are derived. To go there, to escape from this threshold, this plateau, and come below, I need to use times that grow with n exponentially, times something. I don't know what. But these times are not reachable with this calculation. Yes? It's not so clear, exactly. It's, you can argue things about entropic, but yeah, not that clear. It's a fact. It's like, you know, it's the best part of the system to go to. Yeah. Now, you notice that when you see in lectures drawings that do like this, this is wrong, okay? Ludovic, I'm copying your style. So this is wrong. So if you have to keep something in your memory from my talks, keep this. So to go and do these jumps from one state to the other, you would need times which are so huge that these are completely unreachable. This is even worse than in the case of a magnet going from up magnetization to down magnetization. Do a simulation, of the 2D Ising model with certain sizes, and look numerically how long it takes to go from one equilibrium state to the other one. And you will see that very soon it never happens. It takes, the age of the universe for a problem which is simple, which is a domain growth problem. This is even worse, so just forget about it. This doesn't happen. What happens is something more like that in these quenches. Diffusion in these, flat directions in phase space. A mechanism that is exactly realized by the p-spin model, and then some of us believe it's also realized in glasses. Of course, with the fact that this, if one wants to have a complete description of this problem, one should be able to also treat these timescales analytically. But of course, this is too difficult. I mean, we don't know how to do it. But at least we know what we should do. The problem is that we don't know how to do it. Right? So, okay, there are many other things that I could have said about how these two compare, effective temperatures, relations between these, violations of FDT. That link what happens with the response here and there in these non-trivial regimes, and allow you to define effective temperatures. Okay, this would be a full new lecture. I don't have the time to do it, but I want to then conclude with this picture over here, which I think it's useful for the people who do both glassy physics and optimization problems, because as you heard already, this kind of free energy landscapes appear also in those problems. Dynamics would be dynamics of algorithms. They don't necessarily respect detailed balance and all the conditions I wrote to be able to equilibrate. But then you can still look at the evolution of the problems and their weird dynamics and see how they behave with respect to the free energy landscapes that you have behind them, and so on and so forth. OK, so I will stop here. I'm here until Wednesday actually. So if you want to discuss more, I'm around, so we can discuss or even do some of the calculations that I didn't do in detail if you wish. Thank you.